Okay, let's talk about matrix inverses. So, let A be a square matrix, so the height is the same as the width. It's n by n. If I can find another matrix B so that A times B is the identity matrix, then I say B is the inverse of A, and we use this notation. Like it looks like A to the minus 1 power, what we call B the inverse of A. And here is a fact that I'm not really going to prove because I'm not really teaching theory right now. But if that's the case, like if B is A inverse, then of course by definition that means like A times B is the identity matrix. But it also happens to be the case that B times A is the identity matrix, which is not necessarily obvious because, of course, in general, A times B and B times A do not have to be the same thing for matrices. But when they're inverses of each other, it is. Like they're both just the identity matrix. Here is another fact that's important. Not every square matrix has an inverse. So here's a matrix. Let's see that it has no inverse. Well, if this one is my A, and I'm trying to find another matrix B such that A times B equals the identity, here's the 2 by 2 identity. So it's like I'm trying to fill in the blank. I'm trying to find a matrix that goes here to satisfy this. So let's try. Maybe I'll call this like, I don't know, X, Y, Z, W, and try to figure out what this matrix should be. Of course, we have a hint that it's not going to exist, so we should run into trouble. But let's see. Well, we know how matrix multiplication works, so I'm supposed to go across this and down this. So I get 1 times X plus 2 times Z, and that's the top row with the left column, so that should be the top left entry of this, so that should be equal to 1. And let me go, maybe across this and down this, so I'm going to have 1Y plus 2W, and I just went across the top row in the right column, so that should be the top right entry, so that should be 0. And then, okay, this times this, 2x plus 4z should be the bottom left, and 2y plus 4w should be the bottom right. And, well, I don't want to spend too much time on this, but there's a number of reasons why we're in trouble here. For example, I can look at these two equations. These two equations contradict each other. Basically, if I multiply both sides of this by 2, right, this is telling me 2x plus 4z should be 2, but this is telling me that the exact same number should be 0. So, right, we knew something should go wrong because we were supposed to show that it has no inverse. So, we're good. So, here's a quick fact, and again, I'm not going to prove this. I'm not teaching theory right now. But if you have a 2 by 2 matrix, it has an inverse if and only if AD minus BC. So it's like you go across here and subtract, is not 0. And as long as it's not 0, I can tell you what the inverse is. It's 1 over this same number times this matrix. And one thing that's not hard to check is that this times this does indeed give you the identity matrix. And of course, this is undefined if this number underneath here is 0, so it sort of makes sense, but I'm not fully proving this theorem for you. I'm just stating it. But parts of it are not too hard to see. Anyway, how do I find the inverse of a bigger matrix? I just told you how to do a 2 by 2. So what if you want to do a 3 by 3? There is a method. So in the book we're using, it's called the Gauss-Jordan method. But so here's a 3 by 3 matrix, and we're going to try to find its inverse. And I say try because inverses don't always exist. So here's a quick summary of the method. I'm going to go through the details, but basically you take whatever matrix whose inverse you're trying to find and call it A and put it here. And then I draw one of these vertical lines and I put the identity matrix to the right. And then what I do is I take this bigger matrix with A on the left and I on the right, and I use row operations to try to get it so that I is on the left. And then once I get it to that point, whatever is now on the right is A inverse. So that's what we're going to do. So how do I start? I put A there, I put the appropriate identity matrix here, and I say appropriate because it's just like whatever's the right size, and we're doing a 3 by 3, so of course I put the 3 by 3 identity matrix there. And then I'm going to use row operations to try to turn this left side into the identity matrix. So this is synonymous with getting it in reduced row echelon form. Anyway, the first thing I would do is try to get a 1 up here, and I already have it. If I didn't have it, then there's a number of things I could do. I could try to swap 2 rows if I see a 1 underneath. I could also take whatever number's there and divide the whole thing by it, as long as I'm not dividing by 0. But I've got my 1 there, so I'm happy. And yeah, let me, as I like to say, I sweep from left to right and try to get this column the way I want it, and then I'll move to the next column and so on. And then the first step of getting this column the way I want it is getting the 1 there, but I'm good. The next step is getting zeros underneath. And I use the 1 to get my zeros. I'm going to take this row, which needs a 0 there, and I'm going to subtract whatever multiple of this row I need to make that a 0. Likewise, here. Okay. Nothing happens on top. Now let's go. Okay, this better be a 0. That's the whole point. 8 minus 2 times 3. 3 minus 2 times 2. 0 minus 2 times 1. 1 minus 0. 0 minus 0. Okay. 3 minus 3 times 1. Of course, this has to be 0. That's the whole point of me doing this. 10 minus 3 times 3. 6 minus 3 times 2. 0 minus 3 times 1. 0 minus 0. 1 minus 0. Okay. I am now happy with this column. I would like the left side to look like the identity matrix, and at least up to here it looks like the identity matrix. Let's try to get happy with this column. I would like a 1 right here, and I don't have one. I could divide this whole row by 2. However, I am reluctant to deal with fractions if I don't need to. If this whole row was divisible by 2, I would be fine dividing by 2. There's nothing wrong with dividing by 2 here. It's fine if you have to deal with fractions, but it can make our life hard. And what I see is I see something easier. I could swap these 2 rows. So Let me just do a switcheroo here. Of course, as always, this is boring. It's a lot of just copying numbers down, but gotta do what we gotta do. Great. All right, I'm a little bit happier with this column. What I would like, now that I have my 1 where I want it, is I want zeros above and below. Remember, I described this as reduced row echelon form. So when I have my leading term, I want my leading entry. I want my leading entry to be a 1, and I want everything above and below to be zeros. So I use my 1 to get my zeros. So here's a row that needs to change. I'm going to add or subtract whatever multiple of this row, the one with a 1 in it, to get my 0. Likewise here, to get this to be a 0, I'm going to use the 1. Okay, 1 minus 0 is a 1. 3 minus 3, well, this better be a 0, and it is. 2 minus 0. 1 plus 9. 0 plus 0. 0 minus 3. And middle doesn't change. And then this, so 0 minus 0. This better be 0, that's the whole point. And negative 1 minus 0. And then negative 2 plus 6. And then 1 minus 0. And then 0 minus 2. Okay. I am now fully happy with this column. And now up to here, it looks like the identity matrix. So all that's left to do is get happy with this column. So what would make me happy? First of all, I would want a 1 here, and there's an easy way to get that. I don't have it, and I don't see anything I can swap into there. Also, I probably wouldn't want to swap from above, because if I swap from above, that's going to mess up the first 2 columns that I'm already happy with. However, there's an obvious thing to do, of course. I can always divide by whatever's there, or if you like, just call it multiply by negative 1. So let's do an easy step where I just multiply row 3 by negative 1. Okay, bear with me while I write all of this stuff down. Of course, I'm really hoping I don't make a mistake. There's a million addition and subtraction and multiplication operations going on, and I don't want to have to fix this video if I make a mistake. So let's hope. So there I am, and so I'm trying to get happy with this column, and I'm almost there. I like this 1. I like this 0 because I want zeros above. The only thing I don't like is this 2. So I'm going to use the 1 to get the 0. I'm going to take row 1 minus 2 row 2. And yeah, let me emphasize something as I go here. Like, the reason why we use the 1 to get the 0, as I keep saying, is because that's not going to mess up the progress that we already made. Like, this stuff up here, this 1, 0, 0, 1, we're happy with this. We don't want to change it. And by using this row that just has zeros there, when I add or subtract these zeros, it's not going to have any effect on the stuff that we like above. So that's part of the reason why we do this the way we do it. Anyway, going in a little bit of a strange order, but we're going to be done after this step. The left side is going to just be the identity matrix. But yeah, let me not go too fast. I need to actually do these operations. 10 plus 8. 0 plus 2. Negative 3 minus 4. Yeah, and then that's all that changes. So the inverse of our original matrix is that. You can check this. You can check it by taking this original matrix, multiplying it by this, and verifying that this times this is the identity. I don't want to do that in the interest of time, but that's what it should be. And right, let me just say a word about that again. Of course, as I mentioned, not every matrix has an inverse. So if we tried this on something that didn't have an inverse, what would go wrong? Well, we would try to get it in reduced row echelon form, but we would find that the reduced row echelon form is not the identity matrix. Like we would typically end up with a row of all zeros on the left. And if you have a row of all zeros, there's no way to get your 1 the way in the spot where you would want your 1. In fact, you can try that method with this matrix. Like this is the one from earlier that we showed did not have an inverse, and then we showed that using some other way. But we could try the same method that we just tried on this matrix. And you would find that when you get the reduced row echelon form, there's going to be a row of all zeros, and there's nothing you can do. So that's how you can detect that you're trying to find an inverse that doesn't exist. Anyway, let me just end with a couple of facts here. I'm going to tie in the word singular or non-singular from the other day. So for a square matrix A, the A inverse exists only when A is non-singular. And just as a reminder, non-singular means that the only solution to A times X being the 0 vector is when X is the 0 vector. The A is singular. That means that this equation has infinitely many solutions. Non-singular means that it just has the one solution, and then non-singular is when the inverse exists. And yeah, just one quick last fact just to sort of motivate this, like why are we interested in inverses? Inverses are useful for solving equations. If I have a linear system where I write A times the vector X equals the vector B, then if I know A inverse, or if I can easily find it, then I can easily solve this system, and the solution is just X equals A inverse times B. And yeah, so why is that? Well, if I take this and I multiply both sides by A inverse, and I'm allowed to do that. Of course, the order of multiplication matters, but I multiply both sides on the left by A inverse. Like I put A inverse on the left of this and on the left of this. And let me do this carefully here. Matrix multiplication is associative, so I can move the parentheses around. And what do I know about A inverse times A? I know that when I multiply a matrix by its inverse, I get the identity matrix. And what do I know about the identity matrix? I know the identity matrix times anything is just itself. Okay, so I said I wasn't teaching theory, but I sort of just snuck a short little proof in there. So that's the proof that I can solve this system by just taking x equals A inverse times B. And this is potentially more efficient. Like, of course, it takes a significant amount of work to find the inverse of a matrix. If you just have to solve one system like this, it's hard for me to argue that the best method is to find A inverse and do it this way. I don't think it's the worst method, but we already had other methods to do it, like you just stick A and B in a matrix and you get it in echelon form and solve it. However, if you're going to have to solve a bunch of equations like this, where it's the same A and a bunch of different B's, then it might be to your advantage to just once and for all find the inverse of that one matrix A that isn't going to change, and then once you know that, it'll be easy to take that inverse that you already know and multiply it by many different B's.